Good afternoon, everyone. My name is Sam Alshroof. I'm from Olsson Fan Risk from Australia, Sydney. I'm the national manager or the CFD manager for Olsson Fire. We have offices in New Zealand, Australia, and the UK. Today I'm gonna talk about JETFANs and how FDS is capable to simulate JETFANs for car park. So just to start with some introduction about JETFANs, maybe I will just skip this one for the second to introduce what is JETFANs actually. It is a very small device. You can just fit it on the ceiling of the car park, and what it does move the air toward an exhaust or an opening in your car park. It's very different to the traditional ventilation system for car parks where they use ducts, massive ducts across two sides of the car park, and you have to provide higher and lower level to supply air and exhaust air from the other side of the car park. So this is quite charming solution which can reduce cost and maintenance for the car park. So just to brief introduce these JETFANs, it's a high jet produced at the nozzle of the JETFAN, and what it does, it induces the air around that jet. So it's actually gathering smoke and CO from the car park, and it is shuffling it toward an exit. So there is two types of JETFANs. One of them is the steam impulse JETFAN, which is quite common, I think, in Europe and the Middle East. And we have in Australia, it's very common to use the centrifugal JETFANs. From my point of view, the second one is more efficient for car parks ventilation. But again, this is a topic to be discussed by itself. Actually, there was experimental studies has been done by Colt in 2004, which is a very interesting study where they compared a traditional car park ventilation system with the two types of JETFANs. What they did actually, if we can play
this video shows edited highlights from the Colt car park ventilation demonstrations carried out in October 2004 in an underground car park at the Avon Fire and Rescue Service HQ in Bristol. The purpose of the demonstrations was to compare for the first time the smoke clearance abilities of traditional ducted extract and of impulse ventilation systems. The car park is a typical single-storey underground car park measuring approximately 50 metres long by 30 metres wide by 3 metres high. It's fitted with a traditional ducted extract system which provided 10 air changes per hour with extract grills at high and low level well distributed around the car park, as recommended in approved document B to the building regulations. The system has now been running for 20 minutes, and while visibility has improved, it is still poor, and the far end of the car park is not yet properly visible. The second test used the existing extract system, modified to extract from a single point halfway down the car park, still at 10 air changes per hour, with 4 Colt Jetstream impulse fans running to create internal air movement, replacing the distribution ductwork. At the 20-minute time check here, the visibility was much better than in the previous test, and the rear wall was clearly visible. The test was terminated here at 30 minutes, with the car park totally free of smoke. The third test again used the existing extract system, modified to extract from a single point halfway down the car park, still at 10 air changes per hour, with 2 Colt cyclone induction fans running to create internal air movement, replacing the distribution ductwork. At the 20-minute time check here, the visibility was similar to the previous test and much better than in the first test, and the rear wall was clearly visible.
So as you can see, that
the test was terminated here
comparing
at 30
the traditional system with the
totally
JETFANs, it's actually more efficient system to clear the smoke, as well as even if you compare it to the CO concentration coming from the emission of the cars, it's even a good alternative solution to traditional system. So it became more requirement from clients to simulate car parks because when you want to design a car park, you have to provide evidence that your design, your location of the jet fans performance is actually working for the car park. So it's either you can pick the recommendation of the manufacturers, which is a very big question mark if you're going to go that path, or you have to provide a CFD simulation which can demonstrate that your car park is well ventilated. So the first question to ask once you want to set up any model is what's your verification and validation method you use to simulate any type. You know, doesn't matter if it's car park or not, any model, you have to provide some confidence that your model representing whatever you want to simulate. So one of the ideas to verify is, first of all, the code itself, the iteration, and the time step you are using, the mesh, the geometry simplification, and the turbulence model you are using as well. Validation, unfortunately, I didn't find any good source to validate my code. So I thought one of the most important bits is just to make a very simple geometry. I don't want to go that complex. One single jet fan in a small domain, and then just play with the mesh and see what is the outcome of that. So apologies, this is not to scale, so it's supposed to be to scale. But however, what I'm trying to do in here is just to flick a couple of options of different mesh techniques and start to compare them later on with different velocity slices. So in here, what we have a very fine mesh. This is 41.66 millimeter, and the reason why we have this weird number is just simply I picked the 250 mesh as a standard mesh, and I started to divide that by 2 and 3. So dividing the 250 by 3, you'll get that fine mesh, and if you divide it by 2, you'll get the second option mesh, and then this is the 125 mesh, and this is the base case mesh, which is 250 mil. And on here, we start to refine our mesh in different layers. Option number 5 is the embedded mesh, where you have overlapping of the mesh. 6 is just a very traditional mesh, where you just refine it once. Number 7 is exactly the same as before, but we have a bit finer mesh as a base mesh. And number 8 is very coarse mesh, which is the 250 millimeter mesh. Number 9 is we start to vary the aspect ratio of the mesh. So this is a 4 aspect ratio. This is a 2 aspect ratio. This is maintaining the 2 aspect ratio with 2 different mesh refinement. And number 12, what we did is we changed the nozzle itself. So if I'll just go back, this is quite important in here to discuss. This is the nozzle of the mesh, of the fan itself. It's very narrow. You're talking about a 1 meter width by maybe 50 mil or 100 mil maximum as a nozzle. So to fit a mesh within that nozzle is a challenge by itself. So running through the results, the very fine mesh is what's represented on case number 1. And if you compare it with the rest of the results we have on here, maybe number 2 is quite comparable to number 1, but everything else on here is very different. Number 5, actually, I found it to be the worst representative of the result, because simply we have the embedded mesh, and I think FDS, the communication between 2 different meshes overlapping is not as mature as it should be. Running through the results again, maybe the aspect ratio, changing the aspect ratio of the mesh can be somehow acceptable, but on the other hand, you'll find that most of your jet in most of these solutions is just stuck at high level compared to the very fine mesh where you have your jet actually, because of the shape of the nozzle, it's actually pushing the jet 7 degrees toward the ground. And it's very obvious, you can see that only in number 1 and number 2. Everything else, you'll find that the jet is stuck on very high level. So if you want to compare a point in space, just downstream of your car of the jet fan at 1.5 meter above the ground, this is the point I picked. And I plotted all the velocities on here Just to define, I just took all the other solutions. I left case number 1 and number 2, which is the most fine mesh. You'll find they are almost overlapping each other, which seems to be a very reasonable, comparable solution. However, if you look at a different component of velocity on the same point, actually, you'll find as well number 1 and number 2 is still overlapping each other, and every other point, every other solution we have is far away from the correct answer. Similar as well on the third component of velocity, you'll find that, this is all the same component of velocity is just different height. This is 1.5 meter above the ground, 2 meter above the ground, and 2.5 meter above the ground. You'll find number 1 and number 2 still comparable. But on the other hand, if you look at the time required to solve a very fine mesh or second refined mesh, you'll find that we need to solve I solved it only for 20 seconds. That's the whole period I solved it for, which is maybe not enough to reach a fully developed flow at the end of the domain, but it was good enough to represent what I need, just a few meters downstream of the JETFAN. On here, you'll find that you need 2,500 seconds to solve the very fine mesh, which is almost 42 hours, almost one and a half day to solve one single JETFAN for 20 seconds. On the other hand, if you want to maybe coarsen your mesh a little bit, but you want to maintain a reasonable accuracy of your results, you need to run it for almost five and a half hours just to run it for one single fan for a period of 20 seconds. Normally, when Fire Brigade asks for a simulation for JETFANs, we're looking for a minimum of 1,200 seconds. So, on normal car parks, medium or large size, you're talking about maybe 10 to 50 JETFANs. So, imagine if you want to run that scale on your car park. It's a question, actually, which we need to ask ourselves that, do we really need to go that accurate using LAS model, using FDS, for instance, or shall we maybe pick a less accurate turbulence model like RANS or transport turbulence model or any other less accurate turbulence model? But on the other hand, although you compromise your accuracy on the model itself, but it doesn't require that fine mesh, you need to resolve your accurate turbulence model using LAS. So you compromise your mesh with the turbulence model you are using. You will find that maybe using coarser mesh with less accurate turbulence model, you'll achieve much better answers compared to very accurate elite turbulence model with a coarse mesh. So it is engineering judgment. You have to ask yourself before you start any project, what is the suitable tool I have to use? You can use FDS to solve it, definitely. But to get accurate solution, is it the best tool or not? This is the question you have to ask yourself just before run any project on that aspect. So I think this is the conclusion I would like to introduce in here. I will make my presentation as short as possible so I don't miss the coffee at least. I think, any questions?
Yeah, I would like to do a couple of observations. I think you've shown velocities, while it's, I think it would be more interesting to see induced flow, because we are talking about inducing the flow from the flow induced by the JETFAN is not the velocity, because you could have a good volume flow, even the velocities may differ. But I agree with you that in last versions of FDS this was a problem. But I think maybe here somebody can confirm it, that in the last version it's working correctly at the moment. We did our own proofs as well, And with that shroud method that I think Thunderhead published in the web, the JETFAN modeling is working much better, and it's quite correct with even with coarser grids than it was before. I think it's mainly solved this problem.
I think whatever published on the website is very different type of problem. It's a round type JETFAN with a very large diameter. So when you compare it to these type of JETFANs where you have a nozzle 100 mil in height, how many mesh elements you want to fit on that? To crack down any inlet boundary condition in CFD knowledge, you need a minimum of 3 cell size to achieve that, which means that you have to have mesh in order of 40 millimeter, and that order is highly unachievable for any commercial use by the end of the day. So if you want to compromise that, again, I just demonstrated that you can compromise it by having maybe 2 cell size. But again, you reach a point that you start coursing your mesh and you're solving totally different problem by coarsening the mesh. So it's a judgment of where to stop, where to refine the mesh, where to understand how suitable is your mesh for your problem is a question mark you have to ask. We have to ask ourselves actually every time we have to run any numerical model.
I agree with you with the mesh, but really I don't know which version of FDS you use in this study, but
it is the latest one, which is
the
6.5.
latest one improved quite a lot in this case, and we did it ourselves with small JETFANs as well. It was much better, and also if you use the HVAC feature for modeling the JETFAN, you can reproduce velocity at the JETFAN much better than with other solutions.
I think the turbulence model they use now is much better than the static and dynamic one we used to use before. So yeah, definitely there's improvement. I think it can be improved more by with the code developing as well. I'm pretty sure that on one stage it will not be that big a problem.
Okay, thank you.
Cheers.
One more quick question.
To assess the mesh quality and the mesh resolution, there are some hints given in the FDS user guide, like the turbulence resolution, the measure of turbulence resolution, and the evaluation of Y plus to assess the quality of the flow along a wall. Did you consider to
actually to simplify the problem, because I know that FDS is not that great to solve any wall boundary condition. I did put my walls to be as slip wall boundary conditions, so I don't have that issue. I try to reduce the parameters as much as I can, just to make sure that I'm trying to come up with a solid conclusion by the end of the day.
Thank you very much for the talk. Appreciate it. Duchan?